Hi, I'm Shashwat from Paris Observatory, and in this talk, I will discuss the possibility of probing some of the features of fuzzy dark matter using the lens's gravitational wave signals. The contents of my presentation will go as this. Firstly, I'll discuss why gravitational wave lensing is a promising tool, and then I will discuss the quantity which we are usually interested in, which is the amplification factor. For completion, I'll give a very quick overview on what fuzzy dark matter is, and finally discuss the lensing features of FDM and how are these things different from a regular port profile. So beginning with gravitational wave lensing. So first an overview of a typical gravitational wave signal, which is plotted on the left. It has three phases, which is in spiral merger and ring down, and its amplitude and frequency increases in time. So in principle, these sources can be behind a lens, which can be a galaxy, a cluster, or even a dark matter blob, and then a regular lensing phenomena is expected. There would be regions inside the caustic that are close to the lens center, where you would expect multiple images, and as one moves away from the lens center, we can have a single image or the weak lensing regime. Well, in this project, we focus only on the weak lensing regime because uh, there's a higher chance of receiving weakly lensed signal as compared to strongly lensed signal. So what makes these gravitational waves an important tool for studying lenses? The first one of which is the much longer wavelength as compared to electromagnetic signals. Now this would allow us to explore the wave optics diffractive features which are absent in electromagnetic signals because of high frequency. And if you have much longer wavelengths, that would restrict scattering to to an extent. And you can see from the image on the top. So there's a coherent wave that passes through these shapes, and this generates some features on the red features on the plane. It's possible to construct lens from these features, but if you have much longer wavelengths, this can be done much more efficiently. Another important thing is these waves are coherent in nature, and thus allows for observing interference between the geometric optics images, which is absent for electromagnetic signals. Again, these signals are weakly coupled with matter, so they can carry information over very large cosmic distances. And the most important is these gravitational waves can be modeled very precisely. So the plot on the lower side shows information, the signals which is received from Hanford and Livingston. These are two gravitational wave detectors, and this shows how well the numerical model fits to these waveforms. So these can be modeled pretty accurately. And adding on to this, we have also seen that we will see that there's an increase in the number of detections with new observing runs. So O4 began in May, and we already have 6 detections. So it's just a matter of time when we would detect the next lens gravitational wave signal. Now we study the quantity that we are interested in, which is the amplification factor. Now it is plotted as a function of dimensionless frequency, which is the omega. And this dimensionless frequency itself is a function of lens mass and the normal frequency. If you see on the plot, the typical features that you can see is the first peak begins at approximately omega 1, and from there you would see some oscillations. Now these oscillations mark the interference between the multiple images that form at higher values of higher frequencies. But if you look closely at very low frequencies, the amplification is very small. And the reason is that the wavelength is so large that it does not experience the presence of a lens. But as you go towards higher frequency, there's a possibility of forming multiple images and interference between those multiple images. Now, depending upon this dimensionless frequency, we can have three different regimes. The first of which is the perturbative regimes that happens for very low omega, and the amplification is extremely small. So we have shown a time domain waveform, a time domain gravitational waveform, which is lensed by a 3 solar mass. Now this gravitational wave is produced for a 30-30 solar mass system, and you can see that the amplification is not very large. Next is the intermediate wave optics regime, where the amplification factor is computed using this complex integral, and this integral itself is it's you can see that it depends on the time delay or the Fermat potential function, and because of this reason, intermediate wave optics has the richest information because this Fermat potential covers a large portion of the lens. So in this plot on the left, where we show the waveform, we see that there is a significant magnification, but this happens for 300 solar mass. The mass length is 300 solar masses. Finally, we come to the high frequency geometric optics part, where multiple images can be observed separately. And now we see that the lens mass is increased to 3000 solar masses. And the amplification factor is just the contribution from all the different images that form. Fuzzy dark matter. And we know that the CDM simulations can very well explain the large scale structures, but it does faces some of the sub-galactic issues, which are caused before overprediction in the number of satellite galaxies, low mass halos, and it says that the first structures happens at redshift 50, which hasn't been detected yet. But in the case of FDM, we introduce a very light boson particle around this mass range. And what it does, it solves most of the problems that we faced earlier. So it has a flat stable core, which we call a soliton. Due to its quantum nature, you cannot form a halos below a certain mass. And the earliest structures that form now with these FDM simulations are at redshift of 12 and 15, which are in line with what we have observed. Moving features of the fuzzy dark matter. So in this slide, we show the surface mass density, I of tau, and I of tau, which is the Fourier transform of amplification factor, and the amplification factor itself. So focusing on the profile, on the surface mass density profile, first you can see there's this transition that happens, which is the nature of FDM. First, it follows the solitonic core up to some transition point, and then it follows an Amara-Frank white. This width of I of tau is dependent on how dense the profile is. Now, the solitonic cores are very dense profiles, so they have a very narrow peak. FDM does have a solitonic core, but it falls off gradually as Amara-Frank white. So the fall is very gradual as compared to a solitonic core if treated as an individual lens. Another thing that you might have noticed is these secondary peaks in the amplification factors. Now, these are very peculiar to solitonic cores, and FDM having a solitonic core inherits some of these features. Now, we increase the impact parameter and we see the changes, the first of which is the decrease in the height of I of tau and the shift in the peak of I of tau. And consequently, this shift towards lower frequencies for amplification factor. Now, a point that can be made clear here is that this peak, the tau for which this peak happens, is for a Fermat contour that passes to the center of the lens. So if you increase the distance from the center of the lens to the source, the contour that interacts with the lens center also increases, and that itself is tau, and that's how the value of tau increases in these plots. It follows the same trend if you increase it further, but you still have these secondary oscillations. So now we compare this to a regular cold isothermal profile, which is a very famous lens. It has R inverse square fall, and you can see that these secondary peaks are missing in this cold isothermal profile. And the reason as I mentioned earlier, is solitonic cores are very dense, and this can lead to some resonance effects, some waveguide effects, which we are still discussing. So yeah, this is some interesting feature that we would like to observe with the current set of detectors or even the future detectors. So now we plot amplification factor as a function of increasing redshifts, and we do this for two separate halo masks. one of which is 10 to the power 18 and the 10 to the power 9. And now we're interested in looking at these values of frequency for which we can uh, make these observations. So using this formulation as mentioned above, so we plug in the values for the values of omega for which these features exist, and we get the frequencies to be in this range. And very interestingly, these frequencies are well within the sensitivity of LISA. So we believe that it is highly likely that LISA can detect these features and maybe provide better constraints to the lens model. And finally, to conclude, so gravitational waves, the lensing of gravitational waves is highly complementary to electromagnetic lensing that allows us to have a better lens reconstruction because of its wave optics diffractive features. This is one of the things that I haven't discussed in detail. That is, the group has developed a fast and very accurate method to evaluate those lensing features. And from the calculation above, we have seen this that there are some features of fuzzy dark matter that LISA can detect, especially the secondary oscillations. And the next step for this project would be to include the fuzziness to this fuzzy dark matter, which is the interference pattern that happens outside the solitonic core, and finally try to probe these lens parameters. And with this, I conclude my presentation. Thanks.